All right, so here is your typical simultaneous equations problem. All right, we've got a car traveling at a constant 15 meters per second, passes a truck parked on the side of the road. The truck then accelerates at 5 meters per second. So the instant the car passes the truck, it starts accelerating. When and where will the truck catch the car? All right, so if we draw a quick sketch here on where we're at, so the car, if the car is on top, we're going to draw the car on top. We know that the constant velocity, so that would be an average velocity, is equal to 15 meters per second. All right, now the truck, on the other hand, has an initial velocity of 0, but it accelerates at 5 meters per second So what I like to do here is draw a line down the middle of your page to solve this, right? Label one side truck, label one side car, right? Now for the truck, what we're going to do is we're going to try to solve for the displacement. That's what we're looking for, when and where. So we're looking for displacement and time. So we're going to try and solve for displacement, even though we're not going to be able to. So we got v naught t plus 1/2 at squared. Sorry about the horrible handwriting. I'll clean it up here in a second. Now, we know the initial velocity is 0 because it's at rest, it's parked to start with, so that whole term goes to 0. So what we end up with is displacement is equal to 1/2 at squared. Now, what that means is that will be 2.5 t squared, because the acceleration is 5, 1/2 times 5 is 2.5. And so that is our displacement for the truck. Now, we're stuck. We can't go any further. So what we're going to do is we're going to do the exact same thing for the car and then use the information that we know about the displacement and time to help solve this problem. So for the car, we're going to solve for its displacement. We're going to have to use this equation here. We're going to have to rearrange it. So we're going to have to multiply both sides by t, and the displacement will be equal to the average velocity times t, which in this case is 15t. Now, this is where we have some helpful information, because we know that when the truck catches the car, they are in the same place at the same time. So that means the displacement and time are the same. So now we have two equations here and here that both are representing the same thing. We can set them equal to each other. So we will come over here and say that 2.5 t squared is equal to 15t. We'll divide each side by t to get rid of those t's and the t squared. And so now we have 2.5t equals 15. So t equals, I believe it's 6. Let me do some quick math. It is 6 seconds. Now, obviously sig figs, this needs to be 0.00 seconds. Okay. Now, how do we find the displacement? Well, we just go back to the 15t and plug in 6 for t. Well, 15 times 6 is 80. So the displacement will be 80.0 meters. And there are our two answers for part A. Now when we come down here to part B, we want to know what's the truck's velocity when it catches the car. Well, there we'd be looking for a v final at 6 seconds. So basically we're looking at v6. What is v6? So if we use this equation here, this becomes very easy. Vf equals v naught plus at, because we know everything. V naught goes away. That's 0. That's supposed to be a 0, 0. And so then Vf is equal to 5 times 6. And we end up with 30 meters per second. Now, as I said in class, the fact that this is 30 and the car's velocity is 15 is not coincidence. Mathematically, it has to be there. So this is your built-in check to know whether or not you got it right or got it wrong. Okay? Now, come over here to when does the car and truck have the same velocity? So now what we're trying to do is when does the velocity of the truck equal the velocity of the car, which is 15 meters per second. So this would be like our V final, and this, what we're going to define this as. So this would be VF equals V naught plus AT. All right, again, V naught is nothing, so it goes away. And so this is 15 equals the acceleration, which is 5 times T. We can do that math, T equals 3 seconds. Now again, this comes out to be have a relationship with one of our answers up in part A. This is 3 seconds. It's half of 6. That again is how it must be. So this is a built-in, do you know if you're doing it right type of situation. So no, you can't just say that the final velocity is going to be 30 and then work it backwards from there. Right? You have to use the simultaneous equations. This is just a built-in checkpoint to see, do you actually know what you're talking about? Now, oftentimes what they're going to want you to do is they're going to want you to graph this when you're done. So let's graph it. So I'm going to clear all this and let's graph. So if we have a D versus T graph here, all right, the truck, all right, is the one that started at rest. So it's going to initially have a very flat line, but at the end it's sped up. So it's a curved line like so. So this would be the truck. The car, however, was a constant velocity. So its constant velocity is a straight line sloping upwards like so. And this would be the car. We happen to know that the slope of that line should be 15 meters per second because that's the velocity of the car. Now, there's a couple of key points here that we want to label. Right here would be the displacement for when they pass each other. Right here would be the time when they pass each other. And then they probably also want to know, when do they have equal velocity? Well, we calculated, according to the math, it's about halfway. So it's going to be right in here somewhere. But how do we do that graphically? What we do graphically is we look and see where the tangent line is equal to that line, or the slope of the tangent is equal to the slope of that line. So it's going to be, again, right about the same place, and we will call this TEQ for equal velocity. Now, let's say we want to do the V versus T for the same thing, all right? Now, let's draw the car first. Now, the car has a constant slope of 15 meters per second. Remember, to get from D versus T to V versus T, the slope equals the Y value, okay? And so the slope of the car was 15, so that means that at 15, the car has that straight line right there. It never goes up in velocity, never goes down, so it should be at 15 the whole time. However, the truck started at rest and ended at 30. So it should go all the way up there. Now, if we take a look at this, and this is where they're different, when they pass is right here. When they have the same speed is right here. Do not fall into the trap of thinking this is where they pass. An intersection on a V versus T graph shows they have the same speed. An intersection on a D versus T graph shows they're in the same space. So make sure that you are paying attention to what your y-axis is when you do this graph.